All right, so this is a warm-up question, getting us ready for some of the questions you're going to see again on your Friday summative. So think about transformations, and this function is not given to you in anything other than like a graph form, but I give 4 separate transformations that are not at all the same things to each other, and I want you and your neighbor, that works out beautifully since you have neighbors now, I'm going to pause the video. I want you guys to discuss what these 4 transformations mean, and then I want you to share your wonderful thoughts from your neighbor with the class in a moment. But I'm going to pause the video. Does any set of partners want to explain to me what f of 2x is? All right, Daniel, go ahead.
All right, so f of 2x is a horizontal compression.
Very good. Say horizontal compression, meaning it's going to squish in horizontally, right? Something like this. And if you wanted to elaborate on that, a lot of kids tell me it's a horizontal compression of half. Some kids say of 2. As long as you have the word compression, I know what you mean. So let's talk about this graph. What would I be looking for, and this goes out to the crowd anywhere, what would I be looking for to notice that we have a horizontal compression of 2? Okay, it should get skinnier, but something else also gets it skinnier. What specifically is going to change? Yes, if you catch the x-intercepts and see that they're being halved, that's the easiest way to identify a horizontal compression. So like, for instance, this x-intercept, which is currently at -1, where would it be located once it's been horizontally compressed? Yeah, right here at -1/2. And then this x-intercept, which is, I think it's at 6 right now. So if that got horizontally compressed by a factor of half, where is it now? Yes. So that's the first thing. If I suspect there's been a horizontal compression or stretch, I look for whether the x-intercepts have moved off of their x-intercept spot. That's the dead giveaway that you have a horizontal stretch or compression. So any group out there, talk to me about what happens when you throw a 2 in front of your function. Go ahead, Taylor. Very nice. That's the one we're all used to, the vertical stretch of 2, but now we get paranoid because everything's weird now in math. So what are you looking for to change when you vertically stretch something by a 2? The y's are all going to get multiplied by a 2. So some easy places to notate some y changes would be the y-intercept. So like this guy is at 1 point something, so his stretched one would be at 2 point something. And then any maxes or mins that are not on 0. So like this one, for instance, is up at 10. So his stretch would leave him up at, let's call it 20, up here. So vertical stretches are probably, if you guys step back and look at graphs, you can usually indicate vertical stretches pretty quickly just from like looking at them. But they're not going to change the x-intercepts. That's what's tricking some kids, is when the x-intercepts change. They think it's a vertical stretch because it got skinnier, but the x-intercepts don't change. I said that backwards, excuse me. If the x-intercepts don't change, it could be a vertical stretch. If the x-intercepts do change, it's probably a horizontal compression or stretch. So we got to watch those x-intercepts. All right, what about the 2 reflections? Because clearly these are 2 reflections, but they're different from each other. Which one's which? All right, so 2 reflections are what now? Which one's which?
The reflection over the x-axis is the first one.
This one?
No, the
This.
other one.
Ah, this one. Okay, so this is a reflection over the x-axis, which some of you refer to as a vertical reflection. And if you guys think about what it's telling you, when you throw a negative in front of an f of x value, f of x is synonymous with y, right? So it's literally telling you to negate your y's. So any y value, instead of going up 10 units, it wants you to go to -10 units. So that's what the reflections look like on graph, and they literally interpret the same way. Same thing with the other reflection. What happens when you throw a negative inside the function like this? This is a reflection over the y-axis, and if you're wondering what that does to your graph, it literally tells you what it does. It takes all of your x's and it negates them. So this guy, instead of being over here at, I can't read that, 3 something, it's over here at -3 something. So a reflection over the y-axis. All right. Of course, PreCalc is fun, and they usually combine a few different transformations with you on one question. We're going to be doing a lot of transformation warm-ups in the next few days. In your packet, could you find worksheet 12, please? This is our last lesson in Chapter 1. That big old stack of papers over there is the next unit. Woo! That looks great. So, I'm going to give you guys the same spiel that I just had a conversation with one of my old pre-calcers, now calcer, and several parents over the last parent-teacher conferences, right? So I just wanted to communicate this to you guys as well. So here's what's going on. Kids will leave pre-calc successfully, feeling good about themselves, move on to calc. And then I go in and I check on their calc progress, and they're not doing very great. And I said, what's going on? And they're like, calc is hard. I said, yeah, okay. What you doing? You doing your homework? And of course the answer is, yeah. They go, yeah, kinda. And I go, well, why aren't you doing your homework? Well, I didn't have to do a lot of homework in pre-calc. It was really easy for me. So here's the thing about pre-calc. Pre-calc is an extension of knowledge you already possess. So almost everything we talk about is something that you've seen, heard of, learned before, and we just extend it to that next level. Like, we did quadratics, but like more of it. And right now we're doing inverse functions, but we're going to do more of it. Domain and range, just more of it. It's all stuff you've seen, with very few exceptions. We're going to do logarithms, just more of it. But when you move on to calculus, that's not the experience you get. Calculus is a brand new animal, where it is not familiar at all. So for someone to walk into calculus and go, I'm just really good at math and I don't really need to practice it very much. This is the first experience in your math life, with few exceptions, where you're walking into that class with almost no prior prerequisite knowledge other than just good skills. You're walking in with your skills. So obviously some are math skills, like can you factor really well? Can you solve equations really well? Yes, 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 and yes. Do you have good student skills? When your teacher gives you homework to practice that night that goes along with that lesson, are you doing your homework right away? And if you don't possess that student skill, those are the kids who struggle in calc. And unfortunately, it takes them too long to figure out how to not struggle. And then their grade is where they can't recover from it. And then they get a grade that they really shouldn't have. Okay? So part of our progress in pre-calc is, yes, I know you're all wonderful math students. That's why you're here. So now we got to sharpen those student skills on top of our math skills to get ready for calculus and beyond. Got it? There's my spiel for the year. It'll come back, I know it. All right, inverse functions. This is another case of pre-calc where we did do an inverse functions part of the chapters in Algebra 2. We're just going to take it further here in pre-calc. So inverse relations, we're going to be very careful about notation in pre-calc. An inverse relation exists if one relation contains BA where the other guy contains AB. So the big idea for inverses is that X and Y switch. Like if I could have every child in America remember one thing about inverse functions and relations is that X and Y switch. Because once you realize X and Y switch, that opens up everything that is property-based in inverse function land. Because the X's and Y's switch, you're going to see a whole lot of things happen. For instance, the first thing that is of note, and this is from your textbook, not your notes, this red line is the identity function y equals x. This blue parabola is this original relation that they graphed, a little parabola that was shifted down 4. And then this green parabola, sideways looking thing, is this guy, which happens to be the inverse relation to this original blue one. Now, it's as simple as just taking your ordered pairs and switching them. Do you see each of these ordered pairs is just the reverse of the original ordered pair? And then once they played connect the dots, they developed a really beautiful looking relation. Would you call this green thing a function?
No.
Why not?
It doesn't pass the
It doesn't pass the vertical line test. So today we have to be careful about whether you're calling something an inverse function or an inverse relation. You also have to be careful whether an inverse function even exists. We'll get to that in the notes in a minute. But one thing I do want you to note is that these ordered pairs are reflections across this line y equals x. That's one of the definitions of inverse functions, one of the properties. So for instance, this ordered pair right here on the green guy matches up to this ordered pair right here on the blue guy. This is a reflection across the line y equals x, which if you think about like what the math is saying, if you were to switch x and y in placement, that's exactly what you get. You get a reflection across the line y equals x. So in your notes, there's a whole lot of words. I might suggest you guys do some highlighting. I think your notes officially start here, though, where it talks about inverse functions and one-to-one functions. So this part's not in your notes, so I'm going to scribble all over this slide for you. They give you an exponential function looking thing here, this blue guy. And notice I called this blue one a function. Why am I allowed to call this thing a function?
It passes the vertical
This passes the vertical line test. Whoops, that was an L. So since the original passes the vertical line test, the original thing is a function. Well, that's very exciting, but I don't care about the actual function today. What I want to know is whether his inverse would be a function. So then we apply what's called the horizontal line test. So the horizontal line test works the same way. You draw a bunch of horizontal lines through it. Does this one pass or fail the horizontal line test? It passes the horizontal line test. What does that tell you? Who? The inverse is a function. So without even knowing what the inverse looks like, if the original passes the horizontal line test, that means the other guy would have passed the vertical line test, and therefore it would be a function. So you don't actually need a picture of it to know whether it's a function or not. And what's kind of cool about today is for part of your work, sometimes all you have to tell me is the inverse doesn't exist, and you don't even have to worry about finding anything. You just write, does not exist. So, I'll show you. All right, so here's where the highlighting in the notes can start, guys. Two relations are inverse functions if A and B and B and A switch. Okay, so that's the idea for inverse relation, meaning your ordered pairs switch around. This is a big idea today. I'm really picky about notation for pre-calc kids. Your inverse function has to be, you have to use inverse function notation. So if the original was f of x, that means the inverse to it is f inverse of x. But that goes for any function name. So what if they named him g of x? What is his inverse called? Yeah, g inverse of x. So just be careful that the original, what his name is, and then call the new guy the appropriate name. That's all. All right, here's some more highlighting for you. The horizontal line test. What does it tell me about the horizontal line test? So it says, a function has an inverse function if and only if it passes the horizontal line test, is what this is saying. Okay, and here's what I will also tell you. How do you know if a function is one-to-one? If you have a graph and it passes the vertical line test, why can I not make L's today? And it passes the horizontal line test, that means you have a one-to-one function. Let's talk about what that all means though, guys. If your graph passes the vertical line test, you guys told me a minute ago that this means the original is a function. But what does it tell you if the original passes the horizontal line test? That means the inverse is a function. So in order for you to claim that you have a one-to-one function, your graph has to pass both the vertical and the horizontal line test. So there's a question on your test coming up on Friday that gives a graph and it says, is this a one-to-one function? And why? And you'll throw some vertical and horizontal lines down and you'll tell me whether it passes or fails those two tests, okay? So it has to pass both to be considered a one-to-one function. So this is a graph that Mrs. Hoffbar already snagged a picture of it from the calculator. This is a quartic. They want to know whether the inverse function exists. So once you have a picture of it, this is the original, right? Would his inverse be a function? No, because why? It fails the horizontal line test. So because it fails, the original fails the horizontal line test, that means the inverse function does not exist. And for now, you don't have to do any work. You just say does not exist. All right, so normally, if you have no clue of what these look like, you would grab your graphing calculator, but because I want to make sure we get through the lesson, I'm going to just spoil it for you. This rational function looks like this, has a couple of branches. It does have a vertical and horizontal asymptote. We'll learn more about that in the next chapter. I realize the original is a function, but talk to me about whether his inverse would be a function or not. What do you think? Yes. Totally passes the horizontal line test. So all they want you to do is write down yes or no. So yes. That's a nice question. All right, this next one. Y'all know this as your parabola who's been shifted down 5. So that's a big no. fails the horizontal line test. And then this next one, I don't expect you guys to know what it looks like off the top of your head. It starts up here and kind of does like this. So what do you think? Yes. That's a yes. I didn't draw it very well, but it does pass the horizontal line test. So some of your homework questions could be as simple as that. Does the inverse function exist? Yes, no, yes, no. All right, so here's the idea for one-to-oneness. It's passing both the horizontal and the vertical line test. So first you have to decide if what I'm giving you is a function, and does this function pass the horizontal line test as well? If it does, then we can move on and actually find the inverse function. But then, of course, because we're pre-calc, we have to remember everything we've done before this. You also have to remind yourself about domain restrictions. So these are some of the same steps you guys saw in Algebra 2 with a couple of example changes. The first step, use the horizontal line test to confirm whether the inverse even exists. In Algebra 2, we didn't make you do that step because we just gave you functions that existed. We didn't have any trick questions for you. But in pre-calc, we are totally going to trick you. So you have to check that it passes the horizontal line test. The original passes the horizontal line test. Then, once you have that, you guys all remember now that f of x means the same thing as y, right? So they're going to want you to switch the x and y. In my class, we always said switch, but they're using the words interchange or exchange. Once you switch the x and y, you've kind of turned your function inside out, then you're going to solve for y. And this is the part that we're going to be really, really picky about in pre-calc. It's all about notation. Once you've solved for y, don't tell me y equals and that's your final step. You got to name it appropriately. And then this is the big pre-calc change. State any domain restrictions. All right, little recap. There's two things you guys have to worry about when it comes to domain restrictions. Do you remember what they are? Your denominator cannot equal 0. So if you have a denominator with some algebra in it, it can't come out to 0. That would be a domain restriction. And then the other place where you might see a domain restriction is if you have an even radical. Whoops. So like a square root or a fourth root. And remember the square root and fourth root and sixth root, you can't have anything negative in there, right? So whatever's inside of here must be, let's say, greater than 0. Because we're not going to involve i's in our work for this lesson. So it's more elaborate than what you did in Algebra 2, for sure. We're going to have weird functions. So here we go. This one's done for you. It's a very boring example because the original is a line. So you don't have to do any work. They've already done it all for you. They graphed, well, hopefully they didn't have to graph it. Y'all know that this line would pass the horizontal line test? Good job. Okay, so then since it passed the horizontal line test, they said it exists, so let's go find the inverse function. And they found that by, instead of f of x, calling it y, and then they exchanged, or they switched the x and y around. So, whoops, switched. And then they did a little algebra to solve for y. And that's what they have right here. And then they renamed it. So the new function inverse, f inverse, is 4x minus 12, which is another line, which doesn't have any domain restrictions, so they didn't bother doing anything with domain restrictions, because it's a line, and lines are cool. Or boring, whatever you want to talk about. All right, let's look at number 4. This one's not done for you, but can we all conclude that 2x minus 4 would be another line that would totally pass the horizontal line test? So since the function does exist, the inverse function does exist, let's go find it. So first thing you need to remind yourself about is that y is the same thing as f of x. So now you're going to turn the function inside out by switching the x and y. So it becomes x equals 2 times y minus 4. And then you're going to solve for y. So you're going to isolate the y. So let's add the 4 over. And then you can do a big divide by 2 fraction bar, but because this is a line, it would make the most sense to divide everything by 2 separately. And then it's backwards, which always bothers everybody. So let's Start with y equals, I would write a 1/2 x plus 2 when you simplify that. Would it be okay if I stopped and called it y equals 1/2 x plus 2? No, that's not the appropriate name. What should I name this guy? F inverse. Very good. The inverse of f is 1/2 x plus 2. Now, I do also have to watch out for any domain restrictions, but because we don't have any algebraic denominators, nor do we have any even radicals, we don't have any domain restrictions because this is a line. All right, this next guy. Hopefully you don't need your graphing calculator to tell me what this looks like. It's a parabola. Looks like this. Whoops. So step 1, apply the horizontal line test to tell me if the function has an inverse. Well, that's a quick no. So since it fails the horizontal line test, what you're going to write is the inverse function does not exist. And you can abbreviate just like I did. I always abbreviate function FCN. And does not exist is commonly known as DNE in math. So later on in the lesson, we'll discuss how we could technically find an inverse function if we worked with some domain restrictions, but for now we're just going to say it does not exist. All right, this next one, spoiler alert, the inverse exists because it passes the horizontal line test. It's one of those rational function ones again. So we're going to go through the same steps of switching the x and y around, and remember this is really a y. So switching the x and y around, you'd end up with x equals 5 over, and then y minus 2. Now, sometimes kids look at this and they get a little worried because they're like, what am I supposed to do? Well, it's trapped in what you guys know as a proportion. So typically, what do you do with proportions? You cross multiply them. Yeah. So however you want to think about you freeing up this proportion, you're cross multiplying it. So x times y minus 2, I would like you guys to write it as x times y minus 2 times x. And then equals 5 times 1, so equals 5. And remember what your goal is, guys. You're trying to solve for y. So your next step in that algebra would probably be to add the 2x over. So 2x plus 5, or 5 plus 2x, I don't care. And then final step would be to divide everything by an x. Now in this case, you get another weird rational function thing. So I would encourage you guys not to try to simplify this one further. For most kids, the next thing they write down for me is y equals 2x plus 5 over x. And I'm going to have a problem with that. Why am I going to have a problem with that? That's not his name. What's his name? Yes, f inverse of x equals that. And then I'm going to have another problem with you stopping here because we also have a domain restriction. What can x not be? Yes, I can't use x equals 0 because that would definitely be a divide by 0 thing. So instead of doing the interval of like skip over 0 for today, are you guys okay if we just do this? X can't be 0. We can't do that always. Here's what I will tell you. I will let you do this eventually once you guys prove to me on tests that y'all know how to do interval notation. Okay? So if it says write your domain in interval notation, I want to see it that way. Eventually we will be shortcutting it a little bit. That was the same answer first hour had. He said, let's always do that. All right, number 7, the cubic function that was sitting at up 4 for that origin point. This is going to pass the horizontal line test, so you are going to be able to find me an inverse. So let's find the inverse. Switching the x and y around. So kids get nervous on this one because it's unusual to them. They're going to subtract 4 from both sides. And then what's going to be your last step to isolate the y? You're going to cube root it. This is where everyone starts panicking. They're like, what happens when I cube root? Something happens. Well, yes, you do cube root things, and then they're wondering if they're supposed to put a plus or minus down. You tell me, are we supposed to put a plus or minus down? Why not?
I don't know, I just knew no.
So you don't. On a cube root, when do you use a plus or minus?
Square root.
Square roots and fourth roots and sixth roots. What's the difference here?
It's odd.
This is an odd root. So you don't use plus or minus, which means, I'm going to hurry up and name the function the right thing. This inverse function is the cube root of x minus 4. And again, kids are panicked because they're like, well, what about the domain restriction? Because they're like, isn't there something to do with radicals? Yeah, but what kind of radicals? Even radicals. Is that an even radical? No restriction, so no domain restriction. You could write domain negative infinity to infinity, or you could just write nothing for that one. Okay, it's a big note. These are tricky and on the final, and your test, and probably every other test for the next 3 tests. Now, okay. I don't call these tricky. I wouldn't call them fun. They're soothing. Yeah. I think we got to give you guys more credit. We're going to get to a point in the algebra here where you're like, oh man, this seems familiar. There's a trick we have to use in these problems that are like one of the first things we do in Algebra 2. So for my strong math students, which is you guys, you're going to be like, oh yeah, I totally remember doing this. So let's give you more credit. I think you got this. So again, passes the horizontal line test, yay. Let's go find the function's inverse. So the first thing you're going to do is you're going to switch your x and y around. So this becomes x equals, now what's tricky is the fact that they're going to have more than one y in the problem. This becomes a y, as does this one down here. So in math, when your algebra is stuck in a proportion, you free it up by cross multiplying. Alrighty. So if I cross multiply this times this, you can write it out separately with the distribution parentheses, or you can just go ahead and distribute it. But this becomes x times y plus 4 times x. And then the other diagonal is pretty easy. It's just equals y. So I need you to think like an Algebra 2 student again. This is one of the first things you did in Algebra 2 and Honors Algebra 2. You're supposed to isolate for the y, but what's the problem?
When you take the y and put it to the other side, they cancel out.
Do they? Well, I think the first overarching problem is there's more than one y in the problem. Are you guys seeing that? So when I say isolate the y, like that's a little difficult right now. Which one?
Well,
and
one of them's already is.
Well, I can only have one y to the problem. That's the issue. So what your teacher's going to ask you to do is group everything that has a y to one side of the equation and everything that doesn't have a y to the opposite side, and then factor it out. Very good. So are you guys okay if we just move this term over here?
Yes.
Because that's the first step. Your teacher's going to say group them together. So over here, all you have is a 4x. What do you have over here?
4x equals y minus xy.
Yeah. So these don't combine. And this is where Algebra 2 was like, whoa, what now? But Cameron said, now you got to factor. Remember doing this? There's a common y that you could factor out. So if you factored the y out of that expression, you're careful. You're still left with what's y divided by y? A 1 minus x. It's the undistributed idea. Factoring out a common term is the opposite of distributing in a common term. So this equals 4x, right, still? And your job is to solve for y. So your next step would be to divide by 1 minus x. And math says if you do it to the right side, do it to the left side as well. So you're done. Y is isolated. But now you got to get fancy with me. We don't call it y. What do we call it?
F inverse.
F inverse. I like the hoity-toity attitude you gave me on that. And then 4x over 1 minus x. But wait, there's more because it's PreCalc. What's the domain restriction? X cannot be 1. Yeah, that would be a major problem because you'd have a divide by 0. All right, so where I started writing in blue, where I wrote down factor, that's what I was referring to about like you did a whole bunch of these in Algebra 2, where there was more than one of the target variable. You couldn't lock it down yet. You had to factor it out, and then you could divide. And once you got the hang of them, they weren't horrible. But this is what we call algebraic manipulation. These are the algebra skills that you need to progress further in math, and you guys you have them. So that's the great news. All right, let's do the other tricky one then. Since it's on our final, because it's awesome. All right, so switch your x and y around. Remember, this is really a y. So when you switch them up, you get x equals y minus 1 over 2y plus 5. So once again, it's a proportion. You should cross multiply it. If you're having a tough time with the distribution of this diagonal, then you can write it out the long way. Like you can write out x times 2y plus 5, and you can distribute it yourself. I'm trying to, you guys are always looking for time savers. This is one of them, okay? So 2xy plus 5x. And then this diagonal is really boring. It's just y minus 1. So once again, I need you to collect everything that has a y to one side, group it, and anything that doesn't have a y needs to move to the opposite side. So I'm going to pause the video and I'm going to freeze the screen, and then we're going to meet up in like 12 seconds, and we're going to see if you guys match me or not. And don't panic, because there's more than one way to do this next step. All right, so that's what I did to group them around it. Anybody follow me? Anybody do something totally different? The people who said what probably did something different. I brought y's to the left.
How'd you get?
I brought non-y's to the right.
Oh, I'm so.
But did you do something else? Okay, so if you went opposite of that, if you brought the 2xy over to the right, is that wrong? Not at all. These are super fun to grade because there's like 17 different possible answers. That's an exaggeration. There's 4. But there's a lot of possible answers. So the creativity in your math is beautiful and all, but I got to figure out if you're equivalent to me. It's okay. That's my job. I'll figure it out. But I chose to bring the y's to the left out of just like old ladiness where I always bring the y's to the left. But if you guys went to the right, it's fine. Now, from here on out, our work might not match. We're all ready to factor. You guys with me? We can factor out the common y now. I don't know why I switched colors on myself. So we're going to factor the y out. So for me, if I factor a y out, I have y times 2x minus 1. For the people who grouped on the other side, you're going to have y times 1 minus 2x or something equivalent to that. Okay, we're all on the right track. Keep it going. Every one of us has one more step now. We're going to divide both sides by the thing that's attached to the y. So I'm going to divide by 2x minus 1. And other people might be dividing by 1 minus 2x if you're on the other side. So for me, my final answer is named as f inverse. And I'm going to write down negative 1 minus 5x over 2x minus 1. And there is absolutely nothing wrong with that answer other than I forgot to give the domain restriction. What is the domain restriction? X can't be 1/2. Very good. Because you can't divide by 0. So did a little mental or physical set it equal to 0 thing. Here's the fun part. That's not the only right answer. So like, you know, math teacher is going to be able to figure out if you're equivalent. So some equivalent answers, guys, was 5x plus 1 over 1 minus 2x. Totally fine. Obviously, reversing the order would be totally fine. Putting the negative 2x plus 1 in that order, totally fine. So it's not your job to figure out if you have the best answer. You just have to have an answer that is equivalent to my answer, and I'll figure it out. Got it? Questions on that? Hofbauer reviews that to be the nastiest problem on this lesson, but it's annoying. All right. Well, if you didn't like that, you're not going to like this either. So we're going to ask you to verify two functions being inverses of each other. And if two functions are inverses of each other, they undo each other. Inverses in math undo operations or functions. So it boils all down to like when you're a little kid and you learn that adding and subtracting are inverses of each other.
Is that when you get 1-to-1?
They are 1-to-1 because of reflections over the line y equals x. Yes. So what's about to happen now is if I plug one function into its inverse, it magically undoes everything, and all you're going to end up with is equals x at the end. So all of the cool transitional operations, like times 2 multiplied by 5, whatever, it's all going to be gone. It's going to be taken off because of the inverse properties. So here's the trick, though. Verifying is what you're not going to like. It's not hard. Just some of you are going to find it like stupid. It's just like in proof land, where you didn't want to write it, but you had to write it because the proof itself was the answer to the question. Same thing here. You guys are going to have to find out that fog equals x, and you're going to have to find out that goff equals x. And you got to show me. It's not hard at all. Let me show you an example. Right here. Do this one with me, guys. Here's function f. I need a color. There, that'll be easier to see in the notes. And then here's function g. And what we're going to do first is we're going to find fog. And then we're going to find goff. And the math is very simple, but you got to show it to me anyways. So fog starts with function f. And you take the x out of it. but inside of where the x was, you place function g. So that's the setup for fog. And then here's the part that you're not going to like. You guys see that these 2's are going to cancel each other? And then you're like, oh, but so are the 3's, and the answer is x. Show me one step here. You can show me that the 2's cancel, but the next thing I want to see on your paper is x minus 3 plus 3.
What?
I know. You're like, that's dumb. But this is what a mathematical proof looks like. It's your work. It's not hard math. It's just you got to show it. All right, so then g of f would be the opposite of that, where you start with function g, which is x minus, oops, wrong color, x minus 3 over 2. But instead of x, what are you plugging in? 2x plus 3. And again, you're going to be tempted to be like, they all cancel each other. Well, yes, that's the point of the problem. So maybe you simplify one part at a time. So 2x plus 3 minus 3, well, that's just going to be a 2x over 2. And then 2 over 2 will cancel to an x. Check. So your job is to show me fog and goth. Show that they, yes, indeed, do cancel each other out. And that's how you're verifying that they're inverses of each other. It's not a lot to ask of you. I know it looks like pointless procedure, but it does have a point. All right, there's a question just like this on your test, where I give you a graph and I don't give you the function itself. I just give you some ordered pairs, and I want you to create the inverse function. And it's all based on the idea that they are reflections over the line y equals x. So what I expect you to do, and this is from your textbook, but I like these examples a little better than the one that's on your page right now. So just follow with me here, guys. All you have to do, what I do, is I write a line, maybe a highlighter or something, through, where y equals x would be. That was supposed to be a straight line. It didn't turn out. This is going to give me a visual reflection. I'm really bad at reflections. Like this part of geometry, not good. So I resort back to ordered pairs. Remember, the whole point of inverse functions is that the ordered pairs reverse each other. So if this is the ordered pair 0, 3, that means your inverse function is going to have the ordered pair 3, 0. And if this, I'm just going to pick up another one here. If this is the ordered pair, what is it? Negative 2, negative 1. What ordered pair will my inverse function have? Negative 1, negative 2. And then these 2 green dots I'm supposed to connect the dots with, which in a good, perfect world I'd be able to draw a line. Today's not that day. Okay. So now I kind of step back and I look at that horrible drawing and I think to myself, does it kind of look like it could be folded around that red line? And I go, kinda. Gotta remember, Abruzzo drew it, so it's never gonna be good. Same thing here, guys. All you have to do is take some ordered pairs and flip them around. So like, this is boring though, 0, 0. What happens when you flip around a 0, 0? Yeah, 0, 0. And then, I don't know. None of these points look nice to me. Anyone want to pretend they know where this ordered pair is?
30. 30. 7.2.
Okay. I'm going to go with 5. So the inverse to that would just be, flipsies it. That would be 5, comma 30. It'd be like here. And then this is where I have to use my imagination. Oh, gosh. Oh, that's really bad. That was supposed to be curved, and I don't know what happened. It's several times curved, apparently. That was really bad. Okay, so here's what I promised you. The one on your test is going to be like more obvious points and a little easier for you to connect the dots with. That's my point. All right. Like this, I guess. This is not that much better. Can you talk to me about some existing ordered pairs? Like, where do you think this guy is? Let's pretend it's a really large dot and it covers
0, 0.
Yeah, I'm with you. And what about this guy here?
1.
Oh boy. Whoops, 1.
Flipping really easy.
Yeah, what about this guy?
2, 2.
Oh my gosh. I think we need some other ordered pairs. Like, how about this guy?
3, 10.
I don't know.
I don't know.
Just guessing. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so here's the trouble I was about to get into. When I go to reverse all these ordered pairs, what happens when you reverse 0, 0? You stay right there, and then you get this guy, you stay right there, and this guy stays right there. And if I was just using those 3, that's not enough information to create a really good-looking inverse, especially if you're me. Yeah, but like, I need more information than that, right? So 3/8 is going to become 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3.
What?
Aha. So now you're like, well, that's interesting. What about the reflection aspect of it? Remember, it's going to reflect over this little red line. So I'm supposed to connect, but these little like bumps are going to reflect to the other side of the red line. So I'm totally going to draw this well. Watch me go.
Whoa!
Boom! Except I used the wrong color.
Looks like unwinding DNA.
Oh, that's beautiful. It's a helix. Oh, what cool. Hey, that was, I'm going to call that a win. Look at that.
Pretty cool.
All right, so here's the bummer. There's a pretty big topic here at the end of your notes that I'm not going to get to because of the end of class. The good news is, this is as far as I got first hour as well. So tomorrow we're going to start with this very last question on your notes about restricting your domain. And I will warn you, numbers 57 and 58 on your homework have to do with this. So if you can figure it out, cool. Otherwise, hang on. Don't do 57 and 58 until we get to talk again tomorrow. It's not a horrible idea, guys. It's just definitely more than a 30-second conversation. All right, thanks. Catch up on your homework, guys. You got 1.6 bookwork, and now you have 1.7 bookwork.